Hello, everyone. My name is Alireza Ranjbar, and I'm happy to present to you today our work about residual feedback learning for contact-rich manipulation tasks with uncertainty. To start with, I first mentioned basically the motivation behind our work, the impedance controller that we use for our manipulation tasks, and basically I move on to the core part of our work, which is about the so-called residual policies, followed by the workspace where we test our ideas, the experiments we do, and then I finish this presentation with our conclusion and future works that can follow it. So to start with, we usually desire an optimal controller, and regardless of the problem scenario or the application we have at hand, our solution may lie somewhere between model-based approaches or model-free approaches, where purely model-based solutions are usually more data efficient, but also biased to imperfect models. They incur more engineering cost, but also often offer more guarantees, which is in contrast to model-free approaches. We assume actually that we already have a solution available to us, more or less as a black box, and we have done the best we could. And we are still wondering if we can improve this controller. A very common scenario is that we are still left with some tunable parameters that we can maybe use Bayesian optimization or other algorithm to try to improve this controller. Or we may also try take our hand inside this controller, use more engineering knowledge, maybe come back here and try to improve our controller. However, we want to assume that we have also done the best we could on this level also. So we have probably tuned all the parameters that we had available, or we have used all the engineering knowledge that was available to us. We are still wondering if we can further improve our controller, our solution beyond its underlying structure. Before talking about possible answers to this question, I would like to first focus on this part because we want to do the best we can here before thinking about improving what we will have as an available solution. So as said, we have this contact-rich manipulation problem, and it is rather established that regulating mechanical impedance has more importance than tracking motion or force trajectories, which is the main philosophy behind impedance controllers. They offer safer interactions with the environment. They handle instabilities better and more naturally, and the recent approaches have made them more energy efficient. In our case, we basically built our work above a recently proposed manipulation framework, where one of the main ideas, as illustrated in this figure, is that we can simplify the complexity of our problem. We can reduce the search space of the parameters that we have available, and we can also use a graph-based skill formalism to leverage a modular scenario where we can use different skills in different manipulation tasks. And they also extend basically some previous works in terms of impedance controller to Cartesian space. And in our case, we basically have this state machine, a finite state machine. And since our main experimental scenario is about a peg insertion, we have this behavior sequence where we assume the peg already grasped. We move above the peg position, look for contact, search for hole, make some alignment, and then proceed with insertion. And during this sequence, if any error is raised, the state machine is going toward a recovery or reset state. So now we have this solution available to us, and perhaps it's already working in a development environment, but we also know that it's not perfect, and we are wondering how we can improve this. So coming back to the earlier question, a recent algorithm suggests using a reinforcement learning policy that superposes its actions to those of the upstream controllers. So it basically tries to compensate for the imperfections that comes from the output of the controller to basically improve the overall solution. And in our case, since we know the main challenge is about overcoming position uncertainty or orientation uncertainty, we allow this intervention only during these two states. However, When we wanted to, in reality, implement this idea, we still had to take our hands inside this black box controller or inside the state machine to make some tweaks to actually make it possible. And the reason is the following. The reason is that the controller actually sees the perturbation of the policy as external perturbation and will try to resist it. So for example, if our true end effector position is here, an ideal policy will try to apply a force in this direction to move it toward this optimal position, but the controller has a different goal to achieve or maintain and will resist it. It will somehow result in a competition between the controller and the policy. In such case, one may instead suggest modifying the input of the controller instead, over which we may not necessarily have any knowledge about its structure. But for example, if we assume it's about joint position or end effector position, here our controller now sees this virtual position instead of the true position and will apply its force accordingly. However, this algorithm also doesn't come without any limitation. And the limitation that this algorithm has is that sudden or non-smooth actions may not be possible to promote within this algorithm. For example, your controller may not allow sudden or non-smooth outputs, or may filter out the actions that come from the policy, or may be hard, depending on its structure, to learn such behavior. For example, if during insertion, an ideal policy applies a rather high frequency vibration for the peg insertion, this may not be achievable in such scenario, in such algorithm. So no surprise, one can instead basically suggest combining both algorithms that we call hybrid residual reinforcement learning to basically use best of both worlds. So to summarize, we have now these three algorithms, and we may not necessarily have any knowledge about the input or output structure of the controller. But if we were going to assume that we have such knowledge available and we were going to exploit it, we could do so like the following. That is, for example, we could define the action space of the policy in end effector position space and map it to joint position space, or define it in range space and map it to joint torque space using the Jacobians, and here using the inverse kinematic, forward kinematic. The workspace where we test our ideas basically uses two Franco-chemical robots. We fixate the peg on one arm to leverage quicker experiments and use another robot to introduce the uncertainties that we expect in the environment. We have a similar scenario in simulation also, and we should also note that we had to decompose the concave mesh that we had available for the hole, for example, because these physics engine don't actually allow concave meshes, or the convex structure that it will result in the simulation will not result in the hole that we actually want to represent in the simulation. So we had to do this convex decomposition. Moving toward our experiments, we also had an additional layer to leverage quicker debugging and better sample complexity that is called adaptive curriculum. So for example, we have these three experiments. We have 4 training environments, 4 evaluation environments. The training environments always initialize with this difficulty and increase the difficulty by this increment if the success rate in these environments is above this bound. And if the success rate is below this bound, it decreases the difficulty by this increment. The evaluation environments, on the other hand, always have the constant difficulty that is mentioned in this evaluation rule. And here is also the architecture that we use for our reinforcement learning policy. And the reward that we define is basically the sparse reward of 0, 1 if the insertion was successful or not. Moving toward the experiments, in this plot, we basically have the result of our evaluations during our train time. And we always start with a zero-shot evaluation of the controller for a number of episodes without any intervention of any algorithm, any reinforcement learning algorithm. So here, where we have this pure reinforcement learning algorithm, when we start applying the algorithm, we have this very low success rate. And the adaptive curriculum that realizes that the environment is too difficult to learn anything from decreases the difficulty until it gradually starts seeing more reward and then starts learning more, and it increases the difficulty and learn, as we see in this plot. So the next algorithm, that is the residual policy learning, illustrate the sample efficiency here and the residual feedback learning as well, whereas the residual feedback learning has shown better performance for overcoming position uncertainty rather than orientation uncertainty. The end effector range space or end effector position space didn't result in a considerable contribution in these experiments, but for the hybrid residual reinforcement learning, we basically see the superior performance in both cases, as you see in this pink curve. So moving toward the next experiment where we have both uncertainties available, we also see a better performance with the hybrid formulation. And with the same hybrid formulation, if we didn't have the curriculum, adaptive curriculum, the results would have looked like this blue curve. And the reason is simply because we don't have any, we barely see any reward in such difficult environment to learn anything from. Furthermore, we also do another experiment where we use visual inputs to the policy instead of contact forces. And we allow the intervention of the policy only during the first state where we move the peg above the hold position. And we also have two additional parameters. One of them is the so-called buffer steps that basically defines in how many control steps there is no intervention of the reinforcement learning policy, and it basically represents how much opportunity the controller has to resist the perturbation of the external policy, external perturbation, or anything else. And we have also an additional parameter, this a strict condition that basically represents if the state machine is going to be very strict about obtaining a goal, position, for example. Is it, if it doesn't see the objective being achieved, then it will proceed to error and reset. So here we also see that we have achieved a better result with residual feedback learning because it simply doesn't result in a competition between the controller or the reinforcement learning gen. And the more opportunity we are giving to the controller to resist, also the worse the performance is. So these experiments illustrate the contrast better. In our hardware experiment, we couldn't have a training and evaluation environment separately. So we only have a training environment where the difficulty is adaptive. And you see when we start with this low difficulty in the simple scenario, we have this high success rate, but when the difficulty is increasing, success rate also decreases until when we basically fluctuate according to the bounds we have defined in our adaptive curriculum. And we gradually increase the difficulty and learn to overcome more uncertainty, as you also see at this below graph. So moving toward the conclusion, we had the residual policy learning that can apply direct actions to the environment. For example, high frequency vibration can be advantages, for example, for overcoming orientation uncertainty. But it also doesn't allow, for example, a spatial search because it will result in the resistance of the controller. In contrast, we had the residual feedback learning which doesn't have the above problem, but it also doesn't allow sudden or non-smooth actions. And we also have the hybrid residual formulation, which basically has the best of both worlds, but may also be not sample efficient. The advantage of curriculum learning and the sample efficiency was also evident in our work. Future works can include better exploration strategies, more guarantees, and we can also yet improve the sample efficiency, and adversarial methods can also be of interest. And furthermore, sim-to-real transfer was also left for future works. With that, I would like to thank you for your attention.